Hello, I am George McMahon and welcome to JJ's Classroom. In today's video, I am going to discuss with you the introduction of spectroscopy with some terminology. If you like my video, then don't forget to hit the like button as well as to subscribe my channel. So now let's start the lecture. The topic of my discussion today is introduction of spectroscopy, in which the definition of the spectroscopy is, it is a group of methods which include interaction of the electromagnetic radiation with the sample. You know that word EMR, electromagnetic radiation. So here, when electromagnetic radiation is undergo interaction with the sample, that means when it incident on the sample, what happens? The sample undergoes following phenomena after interaction with the EMR. First, that is absorption of the EMR, emission of the EMR, scattering of the EMR. It is a physical phenomena, and also some physical phenomenon based on the optics. For example, refraction, dispersion, reflection and polarization. You know all these words. Okay, when sample undergo interaction with the electromagnetic radiation, two changes are occur. Number one, that is called the transfer of energy from electromagnetic radiation to the sample. That means when EMR is incident or interact with the sample, the energy of EMR is transferred to the sample. That means change of energy between the EMR and sample. Those kind of techniques in which this phenomenon occur, that means transfer of energies occur, those are known as spectroscopic techniques. You know some name of them like UV visible, ultraviolet visible spectroscopy, infrared spectroscopy, nuclear magnetic resonance NMR spectroscopy, Raman spectroscopy, and some of the technique which we discuss in semester 3, that is atomic absorption spectroscopy, atomic emission spectroscopy, and the molecular lumination spectroscopy, that is fluorescence, phosphorescence and chemiluminescence. So those techniques are called spectroscopic technique. Why? Because there was a transfer of energy when EMR is interact with the sample. Next one, that is called the change in a property of the EMR. For example, if the amplitude of the EMR, or we can say that polarization of light, change in propagation, that is the direction of the light, those kind of changes in physical property if observed when EMR interact with the sample, those techniques are known as non-spectroscopic techniques. So here, when a sample, the conclusion of this slide, I can say that when a sample is interact with the electromagnetic radiation, two processes occurs: change in energy, change in a property. If change in energy is there, it is called spectroscopic technique. If there was a change in a property of EMR, they are known as a non-spectroscopic technique. For example, naphthalene turbidimetry, refraction, diffraction as well as dispersion. Now what is a nephelometry? It is a new word for you. It is a technique that is used in immunology to determine the levels of several blood plasma proteins. For example, the total level of antibodies, isotypes or classes, immunoglobulin, okay, and immunoglobulin A. It is important in quantification of free light chains in disease such as multiple myeloma. Okay, that is called naphthalene turbidimetry, the name being derived from turbidity. It is the process of measuring the loss of intensity of transmitted light due to the scattering effect of particles suspended in it. Light is passed through a filter creating a light of known wavelength, which is then passed through a cuvette containing the solids. That is naphthalene and turbidimetry. Okay, part 1. Okay, the light source is here, lens, sample cell is there, and transmitted light through the detector. That is naphthalene. In turbidimetry, the difference between naphthalo and turbidimetry is here the detector is in line. We can say that configuration of the detector is in line. It is in line configuration. While in turbidimetry, the detector is placed at perpendicular to the lens, to the source. We can say that it is perpendicular to the source. Look at here, it is perpendicular to the source, while here it is parallel, in line to the source. That is the basic difference between nephelometry and turbidimetry. Now, what is EMR? It is a form of energy having a dual nature. Consider as a particle means photon as well as wave-like radiation. It consists two electric and magnetic component. You know, that is when there was electromagnetic radiation, it has two components. One is the electric component that is parallel to the propagation of the wave, and another is the magnetic that is perpendicular to the electric field. Now some terminology which we discuss in the spectroscopy, that is called transmittance. Percentage T is a symbol. It is a ratio of radiation after and before passing through the sample. Okay, percentage T, that is equal to IT by I0, where IT is the intensity of a transmitted radiation, I0 is the intensity of incident radiation. Now, what is the absorbance? The attenuation, that means decrease, attenuation in the intensity or power of electromagnetic radiation after passing through the sample. A is equal to minus log T, that is also minus log IT by I0. A is also equal to 2 minus log of T, or A is equal to epsilon BC. That is a mathematical equation, or we can say the mathematical form of a Lambert-beer's law. That is a principle of well-known UV visible spectrophotometer used in physical chemistry, okay, for analysis of the intensity of complex. Absorptivity, absorbance of a sample when concentration is other than molar, that is moles per liter. Okay, so here in Lambert-beer's law, this term epsilon is replaced by A. Okay, it depends on C, concentration. A, concentration of the solution is other than molar, mole per liter, that means percentage volume by volume, PPT, ppb, or any other. It is not molar, mole per liter. Then the epsilon is replaced by absorptivity. That means your equation becomes A is equal to ABC. But here molar absorptivity, that is your epsilon. If absorbance of a sample when concentration is in molar, okay, here the concentration of a solution is in molar. Because of that reason, the term molar absorptivity epsilon is used here. It is a proportionality constant. A is proportional to B, A is proportional to C. When we combine both, one is a Lambert law, another is a Beer's law. A is proportional to B and C. So A is equal to, when proportional is removed, one constant is there, that is called epsilon proportionality constant. A is equal to epsilon BC. That is the Lambert-beer's law. A is the absorbance, molar absorption coefficient, unit is per mole per centimeter, mole inverse, centimeter inverse. Concentration C in molar, and L in many reference book, B is replaced by L. L or B, both are same, it is called path length. I will discuss that in later. Now look at here. When a beam of light is incident, that is your speckle cell, okay, the cell which is used in UV visible spectrophotometer. You fill your solution in this rectangular cell, speckle cell. Okay, so when a beam of light is incident here, what happens? The light is absorbed by the solution. That means the intensity of this incident light and the intensity of the emergent light are not same. Why? Because some of the radiation is absorbed by the sample solution. That means there was a decrease that means attenuation, the decrease in the intensity of incident light, that is called absorbance according to our definition. Okay, and the ratio, that means the ratio of this emergent light, intensity of emergent, or we can say the transmitted light to the intensity of incident light, is called percentage transmittance. Now what is B, or we can say that here L, the distance between these two walls. Look at here, the distance from this wall to this. Okay, why? Because your light travel through this wall of a cell to this one. Your solution is filled between these two walls of a cell, and because of that reason your solution absorbs the radiation between this distance only, and because of that the distance between these two walls, we can say that width of a speckled cell is called path length, optical path length, L or B. And it is majority in cases it is fixed, it is always 1 centimeter. The distance between, or the width of a speckled cell is 1 centimeter. That's why the value of L is also 1 centimeter. So here is a Beer's law. Putting this all together, we come up with the Beer-Lambert's law, that for any particular wavelength, A is equal to epsilon Bc, concentration mole per liter, path length in centimeter, molar absorptivity liter per mole centimeter, and A is the absorbance. One more PPT is there for you to better understand this. Look at here, that is the source, a monochromator, wavelength selector, incident light I0, that is your cuvette, transmitted light through the detector. That is the instrumentation of the Lambert-Beer's law, UV visible spectrophotometer. Now wavelength, the next term of our discussion, the distance between two successive or the adjacent crest or trough is called wavelength. Now what is crest and what is trough? But before that, unit of wavelength are unit of length, like meter, nanometer, centimeter, micrometer and millimeter. So now that is the diagram. Look at here. For any wave, this point, that means above this line, this point are called crest, while these points are known as a trough, and this point on a line of a wave, propagation of wave, that is called nodes. So you can define the term like the adjacent distance between two crests, or adjacent distance between two nodes. Okay, two nodes, or the distance between two trough, that is called wavelength. According to definition written here, the distance between two crests, two adjacent crest or trough, is known as wavelength. There is like shorter wavelength and longer wavelength. If there was a shorter wavelength, the distance between crests are less. If longer wavelength, the distance between crest is higher or maximum. Okay, that is the also one diagram, crest and trough. And next, that is the frequency. Frequency of a wave is its rate of oscillation. We can say that number of waves per second, that is called frequency. Unit is hertz, second inverse. The energy is equal to h nu, where nu is the frequency. Nu is equal to E by h by utilizing this equation, or nu is equal to C by lambda. Okay, remember those formulas, because we utilize those formula when we calculate the numericals, where h is a Planck constant, 6.626 10 to minus 34 joule into second, or 6.626 10 to minus 27 erg into second. C is a concentration. Sorry, here one correction is there. C here is not a concentration. C is called velocity of light in this equation, and the value of velocity of light is 3 into 10 raised to 8 meter per second. So keep in mind, C is not a concentration, it is a velocity of light. C is concentration in a Lambert-Beer law, not in this equation. Wave number nu bar, it is a reciprocal of a wavelength, that is 1 by lambda. That is a wave number. Unit are inverse of the length unit, centimeter inverse, meter inverse, nanometer inverse, etc. Lambda max, the wavelength at which the maximum absorbance take place. Unit is same as wavelength. So here is a diagram. When you plot absorbance versus wavelength, different wavelength, what happened? Look at here, that is the maximum peak point. The point at which the wavelength at which the absorbance is maximum, at that point the absorbance is maximum. That's why this wavelength is called lambda maximum. So friends, that's all about today's lecture. I hope you like the video. If you like it, then please don't forget to hit the like button, as well as for more videos subscribe my channel. Thanks for watching. Have a good day.